Okay, so now let's look at the problem of now we already know one effect of gravity. It's not just the motion of the planets around the sun, but we also know that when we drop an object, there is a force acting on it, and we know that every object has exactly the same acceleration toward the Earth. Now, how can we explain it? But before addressing that question, there is one thing that we have to, there's another problem that we have to address. Now, this Newton's law of gravity, over r squared in the r direction. This is only valid for point objects. Well, this is not a problem for Kepler or the Kepler's law or to understand the motion of the planets, because compared to the distance between the planets and the sun can be treated as a point object, the planets can be treated as a point object, etc. But if we are, let's say, on the surface of the Earth is no longer a point object for us. So we have to take its finite size into account. Now, although it has a finite size, we have been always using the same trick for objects of extended size. We can divide it into very small parts, each one of which will be a point object. And so, since it acts like a point object, we can use this law, and using this law, we can derive some conclusions. So let's look at the shell. Now, in your book, it says that if you are inside the shell, let's see, this is our shell of radius r. So let's say you put some mass at a distance small r from the center. So the magnitude of the force that small mass will feel will be 0 until r becomes large r. Then on the shell, just outside the shell, it will have a finite value, and after that it will just go as 1 over r squared. So here it is Gn the mass of the shell divided by r squared. R being, again, the distance not from the shell, but the distance from the center of the shell. So this is what the force law of a shell turns out to be. Now let's look at first why it is 0 inside the shell. I mean, of course, you can just divide it into very small parts. You can just sum them, convert it into an integral, and obtain this result. But I would like to avoid that calculation. There is a simpler explanation, at least if you are inside the shell. Let's take this point. Let's assume that we are inside the shell. Let me just draw two lines. Well, ideally, this angle over here, let's say delta theta. Delta theta will go to 0. That's the ideal case. But as delta theta goes to 0, this mass over here and all the masses over here, they will be just point-like. So for the gravitational force of this mass and of this mass, I can use the law, Newton's law. They will be almost point-like masses. Let's say this is mass 1 over here, and this is mass 2. Of course, this is just three-dimensional object here. I'm just drawing the two-dimensional projection, but this is a three-dimensional sphere. So just imagine that I have such cones, and these cones, they have a, let's say, a circular base here and over there. Let's say that the distance of this mass from my object is r1, and the distance of this other m2 is from my mass is r2. Now the question is, assuming the mass is uniformly distributed, what is m1 over m2? M1 is the smaller one, so if it's the ratio of R1 and R2, it should be the small radius to the larger radius, R1 over R2. But if this was a two-dimensional object, you can just form similar triangles, and just by using similar triangles, the area of this length over here over this length over here, or if you just imagine that the base of these cones are circular, the radius of the base of this cone to the radius of the base of this cone is just R1 over R2. But the base area is radius squared. Since the mass is uniformly distributed, the masses M1 and M2 are proportional to the areas, the base areas, and the base areas are proportional, the ratio of the base areas is R1 squared over R2 squared. Now what does this mean? This just means that M1 over R1 squared, this is equal to M2 over R2 squared. Well, let's just add some more constants and coefficients. Newton's constant times M times M1 over R1 squared is equal to Newton's constant M times M1 over R2 squared. Now what are these? Well, there is this mass M1 exerting a force on this small mass M, and it will be along this line. There will be this force, let's call it F1. There will be this other force, let's call it F2. This is the magnitude of F1. This is the magnitude, thank you, of F2. So these two forces, they are pointing in opposite directions, but they have the same magnitude. So their sum is just 0. So this is why inside the shell, the net force acting on this mass is exactly 0. Of course, this is just a special case, but you can just imagine drawing these two lines anywhere. I mean, for each mass somewhere over here, there will be a corresponding mass on the other side, whose forces they exert will be identical in magnitude but opposite in direction. Well, things get a bit more complicated. I mean, I did a trick over here. Now let me draw another case. Here is our mass. We can imagine drawing these two lines. But the trick over here is, you see, if you draw these segments, now these objects are not vertical cones. They're the bottom. The bottom is a bit tilted. Now that was the cheat. I was cheating over here because the cones I chose were special in the sense that only in these two cases the cones are almost vertical. The height is perpendicular to the base. You can also make such a choice to compare the force that the mass over here exerts to the force that the mass over here exerts. The base is not a vertical cone, but you can still use similar triangles. You can still do the same trick. The observation is this one, this angle over here. Just take this angle over here. And this angle over here. They will be always equal. Remember your geometry. We have this circle. There is a circle, and we have these two angles that see the same arc. So does it ring any bells? Okay, so these angles are same. So these cones are still similar to each other, although the base is not vertical. Since the cones are similar, the base areas. Again, if you just imagine this R1 distance and R2 distance, here we have M1, M2. M1 over M2 will be proportional to A1 over A2, to the areas of the bases. And since the cones are still similar, the ratio of the areas will still be R1 squared over R2 squared. So always, whichever mass you consider, on the other side, on the symmetrically opposite side, symmetrical with respect to your point mass, there will be a similar mass on the other side, and their forces will exactly cancel each other. So this is why inside the shell there is no net gravitational pull. Well, I will not go to the proof of the other one. I couldn't find any simple proof to prove that if you put this mass outside, it just behaves as if it's a point mass. So if you have this shell, and if you put the mass outside, if this is the distance r, this system is similar to this one. This has mass m, this has mass small m, this is the large mass, this is the small mass, and their separation is again r. So if you have this perfectly spherical shape, in that case it behaves as if it's a point mass if you are out of the shell, and it behaves as if it doesn't exist if you are inside the shell. Those are two limiting cases that we will be using. Yeah, we are looking at from outside. Well, you see, the problem is if you look at the forces depend only on the distances. As long as you are if you are in an inertial reference frame, the distances that any observer measures will be the same to any other observer. So it doesn't make any difference whether you are outside, inside, or upside down. The distances are always the same for all inertial observers, as long as we are in Newton's dynamics.
Can we think the galaxy as a shell and Earth is mass inside the shell?
Well, that was our simplistic model of the rotation curves over here. We just assume that not a shell, but a sphere. Inside is also filled. So this is what we imagined. We imagined the galaxy as a sphere. Of course, a sphere you can imagine as a collection of inner cells, concentric cells, so shells that have the same center.
So the net force on the Earth must be zero?
No. The net force on the Earth is only due to the shells that are between Earth and the center of the galaxy. So let's do that example. Let's take Earth. And let's calculate, let's just imagine some mass m at a distance r from the center of the Earth. Well, you can say that, okay, this is our galaxy and this is our solar system. And the model will exactly be the same. Now, since we have this shell, this sphere, we can imagine this sphere as concentric shells, one inside the other one, filling all the sphere. Now let me. Now the total force acting on this mass m will be the sum of the forces that all of these shall act. Now let's look at this shell, this red one. What will be the total force that this red shell acts on my mass m? Well, I have a perfectly spherical shell, assuming the mass is uniformly distributed. My mass is inside this shell, so the force due to this red shell will be exactly equal to 0. And in fact, it will be the same for this one, because this is also outside of my mass. Let's consider this orange shell. I have that orange shell over there. The force of that orange shell will be Newton's constant, the mass of my test object, times the mass of the shell divided by r squared. Now the total force acting on my object will be the sum of the forces of each one of these shells. M times mass of the shell divided by r squared, sum over all shells for which m is outside. Now you see, for each one of these shells, the small m is constant, that is the mass of my test body. Newton's constant is a constant. R is a constant because they all have the same center, and r is the distance of my test mass from the center of the shell. So I can just take all of these terms outside. So what remains is the sum of the masses of the shells that have a radius smaller than this r. So that it's in the r hat. The magnitude of the force is let's say m times r over r squared. There, r is the mass of the sphere of radius r. Because all of these shells that have a radius smaller than this r, they just make the inner sphere. So here I have the total mass of those shells is the total mass of the sphere. So this is what we have. The total force, the magnitude, is given by this expression. Now let us also assume that the sphere is uniform. If sphere is uniform, mr will be 4/3 pi r cubed times the density, mass density. So this tells me that the force acting on my object is in fact Newton's constant m times 4/3 pi rho. But I have r cubed over here, r squared over here, times r. Does this force law ring any bells? The force is proportional to the distance. So if, for example, you imagine that you have this sphere, you make a tunnel that goes through the center, so you put a mass over here, the force it will be feeling will be in this direction. Let's say this is the x-axis. The force that mass over here will be at the point x will feel will be, it's a one-dimensional motion. The force, if the displacement is in the positive x direction, the force is in the negative x direction. So the force will be minus gn m 4/3 pi rho times x. This is the Hooke's law. So this Hooke's law should immediately ring the bell of oscillations. So this object, this mass, if we would create such a tunnel, And if you just send a mass through it, well, it will burn if it's not crushed, but if we ignore those small details, it will be doing a harmonic motion. And this will determine the frequency of that harmonic motion. Well, the more interesting, more realistic case, by the way, would be what happens if you build a tunnel horizontal one. Well, not a horizontal, but one that doesn't go reach the lava or the center of the earth. Suppose you make such a tunnel. This would be more realistic. You can show that the force, let's say this is the center, so if you put some mass over here, this is the distance x, the force will still be, the magnitude will still be proportional to x, and in this direction, the net force. So even in this case, it will be doing some simple harmonic motion back and forth. Now, there are actually some projects to build trains that would connect two different points just by using gravity. Of course, you have to reduce the friction, you have to lower the drags, etc. But there are people working on that. They are proposing to build some vacuum tubes connecting distant cities and building trains moving on superconducting magnets. Okay, any last questions before we end today? Now, the connection with general relativity we will be discussing on Thursday. Sure. You can first calculate the force created by a ring and divide this shell into a collection of rings and sum all the forces. Well, that's one of the common proofs. Other questions? Okay, see you on Thursday.